we're going to discuss about your subjects too. All right. Last week, we learned about the different types of the circular motions, and I think I repeated like so many times, like, you must memorize this, you must say this all the time. I try to make it really simple in that. So let's talk about the angular velocity, something that I ask you to memorize. Min-chan, how do you write the angular velocity? So I can give you this. This is find it by change in the angle on change in time. But what is the another? Over radius or times radius?
Is it not over radius?
Over radius?
Oh no, it's velocity times radius.
It is velocity times radius. There's something that I ask you to memorize because it was not given in your the formula sheet, but it's useful. You can use any time. All right, Dongyu, what is the whenever we have a circular motion, whenever we have any type of circular motion, what was the conditions? A condition that you need to proclaim. You need to say all the time. Whenever we have a circular motion, in any circular motion, yeah? Yeah? That's not what I said. Aaron, did you watch the video? Did you see I was screaming and yelling? Okay. Oh, thank you. You did. Net force. Any situation you have any circular motion, always the net force is always equal to centripetal force. Always. Whether you have the plane circular motion, conical circular motions, bankings, or like shifting, anytime. That's the one thing. This is the golden key. If you know this, you can do every single circular motion question really easily. So let's discuss some circular motions we learned. One was the pendulum. Oh, let's start from the pendulum we did last week. So it was kind of rotating in this way. Okay. In that case, as soon as you see a circular motion, there's a circular motion made by this pendulum. We know that there is a centripetal force applied towards the center, like this, okay? And then what you need to do is you need to figure out what are the force factors. The factors affecting this is that there are tension force, Ft. There also be the gravitation, Fg, that. So these two are the one making the centripetal force. Yes, Min-chan?
Oh, wouldn't it be omega equals V over R?
Is it V over R? No, VR.
Because that's how I memorize it. It's written there.
Let's confirm, let's justify it. So that is known as delta pi on delta t. So in the one period, it will be 2 pi on t, maybe. The v is known as 2 pi r over t. So using that, oh, so v is equals to then omega r, so other way around. Yeah, you're right. So change that, the v is equals to omega r and r. That's one's method. Okay, let's go back to the circular motion here. So what we know is this pathway will make it. So in here, the net force is therefore equals to Ft, the tension force applied by the string, and the Fg in here too. That is always be equals to the centripetal force as well. And we discussed about this is making an angle of theta, the right angle, like in the right angle triangles. You can talk about how to find Ft and Fg as well too. So it's simple a vector summation diagram too. That's one thing we learned. Second thing was on the road, do you remember in a circular path? Okay, a motorbike or the I'll try my best to draw that. Okay, so there's a shift without and tilting, moving in this direction like this too. We learned that in the plain road, so for example in the roundabout, when the motorcyclist or the driver is turning left or right, there will be a centripetal force applied to the center like this, which is equivalent to the friction force, something we learned as well. Okay, and we also discussed about this why these motorcyclists are tilt when they're turning the corner. So that when they're tilting like this, there will be some angles made. So there are normal reaction force and the gravitational force Fg, and the normal reaction force is made. So you get a help from the normal reaction, the weight, okay, making that angle too. All right, similarly, we talked about the banking. So velodrome, for example, in the banking situation here, and a driver driving like this, coming out of the way and making them theta. And this is the formula that I'll ask you to memorize to me. I'll ask you, Dongyul, do you remember the formula for that? In that case, tan theta is equals to? So as we know, how do we figure out that? There's a normal reaction force applied. Okay, there's a gravitational Fg that's applied there too. But as it's making circular motion, there will be what? The centripetal force in the middle. So what we know here is the centripetal force, the F, the net force is equals to the normal reaction force plus the gravitational force applied. Yep, that is equals to the centripetal force as well. Okay, what do we know about the normal reaction force in terms of the angle? So we can determine the angle here, the theta. So we can make a triangle. So there's normal reaction force going in this direction, Fc, and that's the angle made by the normal reaction force as well. And so it will be actually like this. Adding those factors, this is Fg, and there will be Fc. So that's an angle made by that too. So from here, what we know, you can use the tan theta, or the tan theta is equals to Fc on Fg. Yep, isn't that something we did last week? Yep, and then you can figure out Fc is equals to mv squared over r times that 1 over mg. So that mass cancelled, so you get v square over rg. What's that? Tan theta. Something that I ask you to memorize too.
Doesn't matter if you memorize it as F
Yeah, should be fine. But you can get a questions about v. Then what if the v is equals to rg tan theta and the square root of that too. All right. Up to you finish the HSC or in the HSC trials, the justification showing this working out is pretty common. They can ask you questions like this: hey, why do we prefer using the banking, the cycle like in the race, rather than there's a plane surface like that? And we discussed that in the case, I'm assuming there these two cycles are moving at the same speed, okay? But this requires a huge amount of friction. Whereas that requires because of the banking effect, you will minimize the friction force. So therefore, it will be much beneficial, and it will decrease the more, and give you more assurance on the safety issues too. All right, that's where we up to last week. Everyone good? Okay, and kind of understand? Are you okay with these concepts? Not too hard. I'm just using the module 1 and 2, the vector diagram again too, here. So let's finish up the rest of the chapter 3 today on your page 69. So we're going to talk about a few cases, specifically talking about the roller coaster in that case. So on your figure 5, you see that there is a person riding on the roller coaster, as you can see that, okay? Now, if the person is moving at a constant speed of 4 meters per second forward, Minchan, what can you tell me about the net force applied on this person? If the person is moving at a constant speed of the 4 meters per second, okay, forward, then what can you tell me about his net force? Constant speed?
0.
It'll be 0. It's given here. Net force is 0 too. Why? As we learned, when you're moving at a constant speed, there is no acceleration applied. There's no change in velocity. Therefore, it'll be the 0 in the net force value too. Something very simple. Now, I want you to imagine in this situation here then. We learned about this last time. Assuming that you're on the top of this person here, the roller coaster or the trolley is on top of the hill. Saying that is 10 meter, like this. Okay. Aaron, what do you expect when this was moving in, say, 4 meters per second? I'm using that 4 meters per second here. Now it's going down, or making like some kind of circular pathway like this. So you just see like kind of quarter circle pathway. Like this is what actually happened in roller coaster riding too. So if that's a 10 meter, and if the roller coaster is moving in 4 meters per second initially, what would be its final speed over here, here? How do you find that? Assuming that mass of that is, I give it 100 kilo, 100 kg for the roller coaster. How do you find the final velocity of the trolley at the bottom? Yeah, give it 10 meter height. Not too sure. How do you find the final velocity of the trolley? Going downhill. We use this. The total mechanical energy will be always be the same as a U plus K. Displacement, maybe, yeah, you can, but I would not to, because that would be like a vertical and horizontal. It would be more complicated. Rather, you use that. Now, what can you tell me about U at the top? At the top, at the 10 meter, U was initially mgh and plus half mv square. Okay, so that at top, we can find that m, 100 m times gh, so 100 times m comes at the front, 100 times g, 9.8 times height, 10, plus the 2, half times the v, which is the 4 square like this. This will give you the total amount of the mechanical energy applied here, so 9.8 times 10 plus 4 square divided by 2, and then times 100. Total amount of energy should be 10,600 joules at the top. Now, at the bottom, Minchen, what can you tell me about its mechanical energy? The EM. At the bottom. Will still be the same amount, according to the conservation of energy, 10600 joules. But what change is the gravitational potential energy being converted into the kinetic energy, so there will be increase. So there will be what? At the bottom here, the U would be 0. Yep, so what we know is 10600 purely equals to K, that's half mv square. Then V would be equals to what? 2 times 10600 divided by 100 and square root of that. Yep, and then it will have the 2 times 10,600 times divided by 100, square root of this. Then the trolley is now moving in 14.5 meter per second forward. But, Minchen, at the bottom over here, for this trolley, is this trolley making a circular motion? Is this making a circular motion? When you're going downhill. When you're going downhill like this. Or have you ever experienced like going there, taking the roller coaster ride? So going no, oh, never. Oh. Okay, what did you do in your teenage life? Have you? Yeah. So do you remember like what happened even in the Luna Park? I know that's a pretty dangerous one, but too. Okay, when you're going down the roller coaster, do you remember what happened to your body? Do you feel like much forward? But did you feel heavier or lighter? Well, why do you think we need to wear the bar in the roller coaster?
Is it because we accelerate to the center?
Yeah, you get. Oh, he's gone here. Anytime you have a circular motion, anytime you have circular motion, I take that as a circular motion too. But you should know the difference between that, okay, the plane going the roundabout to going downhill. Downhill is applying some of the gravitational potential energy, but this is still using a bit of the what? Your the circular motion content here means that in that situations the net force will be going upwards too. A means that you are applying some net force on you too. Then let's analyze what type of forces apply on the downhill. So I draw the trolley at the bottom like this, going in the 14.5 meters per second. Okay, what are the two forces are acting on this trolley? Minchen. Whenever we have a trolley like this, there is, yep, from the center going down, so W, mg, yep, the normal reaction force that is going up. But do you think the normal reaction force will be same as the wave force in that case? Maybe not. Yeah, in that situation, the normal reaction force will be same as that, the gravitational force too. But here, I said no. Okay, let's think about this. Any circumstances, any situation you have a circular motion, what is the net force again, Dongyur? Fc always be equals to the Fc. But where is what is the direction of Fc here? In that going upwards. So that is the direction of the Fc. That's the net force as well too. Now I'm gonna play with a bit of a sign convention here. We have upwards. So you can see that normal reaction force is upwards too. So R is that is equals to R, which is a positive, plus minus mg. Yeah? I gave you that 14.5 in purpose to find the normal reaction force. What would be this? mv squared over R. Then, what can you tell me about R? That R would be the mv squared over R, and move that to here, you get plus mg like this. Yeah? Do you remember we did that kind of similarly for the elevator? Yeah, similar things happen here. Then what can you tell me about the R value? It'll be, let's talk about this. Without using quantitative here, Ari, do you think R would be greater or smaller than mg or same? In that case, as R is equals to mv squared R plus mg, do you think R will be greater or less than mg? Just pure. It will be greater. As we have adding this to the mg, so it will be greater. What happened to your body when you're receiving the greater normal reaction force? As you're like kind of pulled upwards too. Someone tried to pull you up. So what do? There's a kind of action force acting on you. As you are reacting against the reaction force, you will be applying the reaction force going down, which means that you will feel heavier. Or if you have any experience like going downhill, you actually feel experience. Oh, going the airplane, going down and going arriving, you actually feel like you get squashed. There's no one actually pushing you down, but you feel like you get squashed when you're going down. Did you feel that? Did you feel that? Have you feel that? Have you? What have you done in your life? Oh, okay. So you never play the bicycle going downhill?
Well, I have.
Yeah, okay, there we go. Okay. How do you feel like when you're going downhill in the fast speed? Did you feel like you're about to fly off, or you feel like you get squashed? If you don't have that experience, you can't remember that. Okay, you're getting your holidays coming. Make sure you get some experience of the circular motion. Scientifically and theoretically, what you should feel is you feel more like a squash. As you get the greater normal reaction force from the gravity, yeah, which makes you feel like I'm reacting to that. So the reaction of the normal reaction force will be going down. So you feel more heavier. You feel great. You feel like being squashed. Okay, that's when you're going downhill like this. So it's given here on the roller coaster diagram. It's actually uphill, going downhill like this on your page 71. Okay, let's draw the vector diagram on your page 71, the bottom one first. So you will see that there is a mg moving downwards from the center. Okay, there will be normal reaction force going upwards too, but there will be in total net force, which is same as equivalent to the FC like that. And then you can copy it there, you can write it down that in that case, the F is equals to R, plus I just copy that down here again, to minus mg, which is equals to mv squared over r. Therefore, R will be equivalent to mv squared over r plus mg, and which makes the R will be greater than your mg, which is the wave force. Make sense to everyone here? For the when you're going downhill like this. Okay, let's do that for here, the one on the top. All right, what are the forces acting on the people on the top here? This is kind of weird, like you kind of hanged under the top of the roller coaster. Yeah, well, we have that actually. Okay, I don't think we have it in Sydney, but I'm sure we have that in Queensland somewhere. Okay, so you can have a chance to get experience. But let's think about what type of the normal reaction force they would experience. First of all, what are the forces acting on these people here? These people hanging. So let's specifically this person in the middle. There will be mg, so straight down from here. Mg, very good. What else? What can you tell me about the normal reaction force? How do you define a normal reaction force? It'll always be perpendicular, normal to the surface. To the surface. Here, the surface is here. So what would be the direction of the normal reaction force? It's going downward too. R is going downward too. As they're hanged backwards. So always, normal reaction force always be perpendicular to the surface you're touching. So they're touching backward like this. Yep. Now, what is the direction of the centripetal force in that case? This also be going down, Fc. That's equals to this net force 2. So shall we add up everything here? So the net force would be equals to minus Fc. I'm just following the direction too. That is equals to minus R plus minus mg. That's minus indicating the direction which is moving down. Then R therefore is equals to Fc minus mg, or mv squared over r, you can say. Do you guys get the point here? Okay, Dongyul, then what can you tell me about R and mg, which will be bigger? Do you think mg will be bigger or R will be bigger? mv squared, yeah. So if that's big, if that's huge, then it's a huge, that minus that, R will be bigger. But if most in general case, mg will be greater. So do you think you will feel lighter or heavier in that situation when you're hanged? You'll feel lighter. So this is why you feel, as you feel lighter, you feel like you're going to continue falling off. This is why you need to wear the safety bar. Yep, there's another situation. All right, what about the third one? Let's move back to page 70. I should start from 70 here. Can you guys draw the vector diagram for this situation here? And then considering which will be bigger, mg or r, and so that you can talk about the whether you feel heavier or lighter. Oops. So it'll be step by step again. So started from the bottom here. Let's say assume that this person here, okay? Well, he or she will experience the gravitational force, which is always be downward like this. Okay? Now, what is the direction of the normal reaction force in that case? Yeah, it'll be perpendicular to the surface touching, so it'll be going up. That's a normal reaction force. But what is the direction of the centripetal force when you're going down here like that? That'll be this. It's a net force that's equals to the centripetal force there. As you're going on the top of the circle, going down like that. Then, adding all of those up, you'll see that the net force is therefore, as we're going down for the centripetal force, it'll be minus Fc. Yep, which is the addition of the R plus minus mg. Then R would be what? The mg minus Fc. Alright, then is R bigger than mg? Yeah, R would always be greater than mg. So what do you think? Do you think that these people would feel heavier or lighter? They would feel, if you have a greater R, you can just remember, greater R means that you do actually feel heavier than what you think in the normal plane. Yeah, they will feel heavier in that situation too, which is making them to more squished. So it's, if you think about a roller coaster too, when you're going downhill or in the slides too, you start to feel heavier. Okay? You feel like you get quite squished until you're going down on and downhill too. Yep, so this is another application of the circular motion in the circular track like that. So on page 72, it's showing you that different type of the circular motion, and explanation is basically I showed you that before. So you'll see that in the situation that down here, the F net will be applied up as the circular motion, the centripetal force is applied towards the center, and then gravity is always moving downward like this. So normal reaction force, as you can see, will be greater. Means that the people on the roller coaster would feel heavier. Okay. On the other case, when you're upside down like that, the normal reaction force will be greater and smaller than the mg, so it will feel lighter too. Okay. What I'm just doing here is I'm just playing with the vectors again. I'm just playing with the directions. There's nothing more special than that too. So let's have a look at the question there, 3.6 on page 73. A skateboarder, mass is 60 kilo, enters the half pipe at the point A, as shown in the figure 7. Assume that there is no friction force, or the friction force is negligible. A, what is the skateboarder's speed at point B? So how do you find that? Use the total mechanical energy is same as U plus K. Therefore, and that at A, that's same as mgh plus half mv squared. Assuming that the skateboard is about to going down. It's not really skating, like about to going down. So that means this makes to 0. And the height of that pipe is 4 meters. So that this equals to 70 kilo of the 60 kilo of the mass, 60 times the 9.8 times the height, which is 4. Okay, finding that, you'll get 2,352 joules for the total mechanical energy. So at B, there is the height is 0, U will be 0 too. Therefore, we can say the total mechanical energy will be purely equals to the K. That is equals to half mv squared. Therefore, the velocity will be equals to the total mechanical energy 2352 times 2 divided by mass 60 and square root of that. Then you get the velocity at the bottom at B would be 8. Let's fix that into 2 suffix, 8.9, 8.85 meter per second, and 3 suffix. There's nothing special. This is just module your year 11, module 1 and 2, module 2. But B would be special now. What is the net force on the skateboard at B? Then net force. Mention in the net force at B. What would be the net force at B? In the circular motions, the net force is always be what? Centripetal force, Fc, which is mv square over r straight away. Do we know the mass? We do, 60. Do you know the v? We just found it, 8.85. Do we know the r? Yes, it's given, it's 4 meters for the radius. That will give you the net force value, so 60. So you can use the exact value saved in your calculator. That times 60 and divided by 4, you should get 1176 Newton. That's for B. C. What is the normal reaction force on the skateboard at B? So let's draw the skateboard at B, or person on the skateboard like this. Okay, the forces applied to him, to her. Okay, there will be mg applied. There will be normal reaction force applied, and the direction of the centripetal force would be up. Yep. So combining them, we can get like this. The net force is actually equals to the direction of the arm, the positive direction r, plus the minus mg as in moving negative direction, which is the same as the Fc2. Yep. So r would be simply equals to Fc plus mg. Do we know the Fc? Yes, we do. So 1176 plus the mg. How do I find mg? 60 times 9.8. Then you get 1764 Newton. Direction of a normal reaction force, upwards. That's the final answer. So, nothing really special. There's only one special thing is the centripetal force in here. That's something that you should remember. Any circular motion, the net force is equal to the centripetal force. What I'm just doing here is I'm playing with the direction. Once you realize that this is very similar to your vector diagram you learned in the module 1 and 2, it shouldn't be a big problem. Okay? Alright, could you guys try the next question 2, passenger question, and up to 3.8. So up to page 76 now, please. 74 and 76. Oh, actually, can I actually collect your homework, please? Yep, we gotta go through some questions. Thank you.
What's that homework?
Yeah.
I didn't know if we were at the back.
Yep, it's okay. Yeah, we gotta go through some. Oh, she?
I didn't know that one was homework.
Did you do it?
Oh, I'm pretty sure I've done it.
Didn't bring it?
Yeah.
Ooh, that was handling homework.
Sorry?
That was a handling homework, so you need to handling so I can mark it.
Was it last week's homework or?
Last week's. Do you have the paper with you now or
Oh, no.
at home?
Yeah, probably at home.
Can you bring next week? Guys, did I give you this last week? Did anyone get this? No? Didn't get one? Okay, alright. Yep, no worries. Thank you. When you're finished, Excuse me. Finished? Okay. All right, let's have a look at the question 3.7 first. A passenger is in a roller coaster car at the top of the circular arc. At the top of the circular arc, a radius 9 meters. So you have to think about the situation where roller coaster at top of the here, okay, and it's moving forward, and the radius is given as 9 meter. A, at what speed would the reaction? At what speed would the reaction force on the passenger equal half their weight force? So, in that situation here, we need to think about the speed, the situation of the forces acting on. So first of all, there are normal. There will be greater. Sorry, the weight force mg moving downwards. The reaction force will be still moving upwards here, and then the Fc, which is equals to the net force will be acting downwards in that situation. Got up to here? Okay. So let's start it like this. The net force applied in this situation here is minus Fc. That is also equals to the mg minus mg plus the r. Then we can make the formula for the r like this. R is then equals to mg minus Fc, that is equals to mv square over r like that. Everyone good over here? Okay. Now, given condition here is what speed would the reaction force equals to half of their wave force. So what we're given here is r is actually equals to half of the mg. There's a given conditions here. So I can substitute back here, making it into half mg. That is equals to mg minus mv square over r. Everyone good up to there? Okay. Then I can cancel out all the m's. Everyone good? Yep. Then move the in the subject to the v. Then v would be half g minus g, or moving that to g minus half g. Okay, and times that to r, and square root of that. That r is given as 9 times that 9, that would be half g, which is 9.8. So I would just put that into 4.9 in here, and square root of this. And what you should get is 9 times 4.9 and square root of that. You should get the velocity of 6.64 meter per second. Good? Yep. Kind of tricky. It's more a math question rather than physics, but we're using that concept of the factors, concept of the normal reaction with the wave force to figure out the velocity. Okay, next one, B. What happens to the reaction force as the speed increases? What happened to the reaction force then as we increase the increasing the velocity would increase what? Would also increase the Fc value. Then what we know as the R is equals to mg minus mv squared over r, which is the Fc value here. As you increase the Fc, as R value would be, in that case, increasing that would make the R would be decreased. Yep, kind of magical logical sense. Increasing this, as mg is a kind of fixed value, then minus that would always be decrease the R like that. That's B. C. What would the passengers experience? So as we, I think B and C will be related. That what happened to the passenger, what if the passenger as the increase in the velocity? As the R is decreased, the passenger would feel lighter, as there is a less normal reaction force applied. So what they actually feel like, they are feeling like they're about to falling off, like they're flying. Indeed, they're flying. Last one, D. What has speed would the passenger feel weightless? So weightless means that when the normal reaction force, there's no normal reaction force, no or the absence of the R, no R. Okay, when there's R is a 0, then as the mg, then mg would be simply equals to mv squared over r. Makes sense? Okay, can we just cancel the m? We can. Then v would be g times r and the square root of this. That g was given as 9.8 times the radius of the 9 and square root of this. You're going to get 9.39 meter per second. It means that the roller coaster will like kind of out of track, or the passenger will be like out of the field too, so out of the track too. That's the answer for A, B, C, D. Question 3.7. Next one, question 3.8. A student arranges a toy car track with the vertical loop of the radius 20 centimeter. A toy car of the mass 150 grams is released from the rest and the height of the 1 meter at point X. The car rolls down the track and reaches the bottom of the loop point Y and the travels inside the loop to reach the top point Z. Ignore the friction. So let's draw the diagram. Question A, relevant informations. So what we have to start is the vertical loop is 20 centimeter. So in here, the vertical loop, something like this. We the loop, the radius of 20 centimeter, given like that, okay? And the toy car is a mass of 150 released from the rest from the height of the 1 meter. So there will be 1 meter. So you can see like toy car is released like that. So you can see the toy car located on the top of the loop here. Okay, and this is given as 1 meter. So you can imagine that this is the point X where the car is now released at 1 meter. At point Y, is it here? This is point Y when the car, toy car, located in at the bottom of the circular track. Like this. And the top, you can imagine this is going this direction. So going in this direction, going in this direction like that. That's A. Yep. Showing all the relevant information means you need to show all the points, X and Y, 1 meter and 20, and every single point and the radius too. B, calculate the speed of the car as it reaches the bottom of the loop and the point Y. Again, very similar questions that we did on the roller coaster. So thinking about the gravitational potential energy and this kinetic energy too. So I show the full working out for this. At point X, the total mechanical energy would be equal to U as the velocity is 0, making it to K to be 0.2. Right, in that case, potential energy mgh is equal to the mass of the car was given as 150 grams or 0.15 times that 9.8 times the height, which is 1. Then calculate that, you get 0.15 times 9.8, that's 1.47 joules. So at Y, the vice versa, there's no, the U as the height is 0, therefore EM will be purely equals to K, that's half mv squared, this is 1.47 as well. Then V will be square root of the 2 times 1.47 divided by 0.15 like that. Got everyone? Yep. So that times 2 times 0. And square root of that, you should get 4.43 meter per second for the answer at point Y. Okay, C, calculate the normal reaction force from the track at point Y. So you can see the track, the toy car, we're now experiencing the centripetal force. So there will be gravitational force, mg, going down, and the normal reaction force is kind of pushing it up, and there will be greater Fc, and that's equals to the net force value. So using that diagram here, yeah, I recommend to draw down the vector diagram so that you can figure out the direction easily. Yes?
How did you get FC direction?
Circular track? Down? It's down here. Why? Then it'll be always centripetal means that towards the center. Where is the center? Here.
If the toy car is outside.
Yeah, same. Doesn't matter. What did I say? Any circular motion, any situation you have a circular motion, there will be centripetal force, which means that acceleration is acting towards the center, always. Whether you look at a cover here, or even this, even that, it will be towards the center too. That makes sense? Okay, so you probably get confused like when you place the car on here. But these two have the same net force acting towards the center, but only difference between these two are the direction of the normal reaction force. That's one thing that's important. So in that case, the net force using the direction convention again too is a positive. The Fc is equals to R minus mg like that. Okay, what's the question C? Asking you normal reaction force. So R is then equals to Fc plus mg. That's mv squared over R plus mg that. Let's substitute all the value. 0.15 times V was given at 4.43 square divided by R. So radius is given at 20 centimeters, means you need to convert that into meter, 0.2. Okay, plus the 2, m, 0.15 times the 9.8. Then 0.15 times 4.43 squared divided by 0.2 plus 0.15 times 9.8. You'd get 16.2 Newton. Direction of the normal reaction force is upwards in that situation here. Okay, Z, at what is the speed of the car as it reaches the point Z? I need more space actually. Use that space given here. At Z, what you see is car is kind of hanged inside of the circular track here. So I mentioned, do you think the car will now carry some gravitational potential energy at here? Yes, there will be some gravitational potential energy and as well as the kinetic energy, but it will be the same amount of the EM, the mechanical energy, which is 1.47. So what you have to show that is for D, the EM will still be the 1.47 joules. That's now equals U plus K. The U is given as what? mgh, so mgh plus half mv squared. The m is given as 4.15 times 9.8 times that h is the diameter. As a 20 for the radius means it's a whole 40 centimeters, so it's 0.4. Plus that 2, half times 0.15 times v squared, given, we don't know. That's something we need to find. Yep, so then 1.3 is equals to 1.5, let's find the value first, 9.8 times 0.4, that's 0.588, and move that, 1.47 minus 0.588 times 2, and divided by 0.15 and square root of that. Yep, so 1.47 minus 0.588 times 2 and divided by 0.15 and square root of that. You get the velocity of the car. A toy car would now be 3.43 meter per second. That's the answer for D. Speed, yeah, it would be the speed. Yep. Now E, what is a normal reaction force applied? So I'm going to use the diagram here again, so the same space for question E. So the car is now kind of hanged on the circular pathway like that too. So show that vector diagram. So the car is now hanged means that there will be some reaction force, I think this mg moving downwards too, as well as normal reaction force and also the net force too. That's Fc. So showing that everything, the net force in that situation here is minus Fc. That's equals to minus mg minus r. Yep. So simply, therefore, r would be equals to, moving that, Fc minus mg like that, which is equivalent to mv squared over r minus mg. That's m, 0.15 times v, that value, 3.43 square, divided by r, r given as 0.2, minus the mg, 0.15 times 9.8. Yep. So that's 0.15 times 3.43 square divided by 0.2 minus 0.15 times 9.8. You're going to get 7.35 Newton. Direction is now downwards. Final answer. Confused? Your admission? You're okay with this? Okay, then can you work out to find that? Yep. So I'll rewrite that for you. The net force is therefore minus Fc, that is equals to minus R minus mg. And we can get R from there. Yeah, so this is the part that I'm kind of duplicating the extension 1 math, mechanics, circular motions like this. So it's good to know some of these contents too. So this is why the year 12 student who left. Okay, who has heard about something called torque? Torque. Min-chan, have you heard about something called torque? No? Okay, torque is really commonly used in engineering. So if you decide to do like mechanical, any of the engineering in, or if you're taking engineering course in year 11 and 12, anyone? Oh, none of you. You do? Okay.
Yeah.
You haven't heard about torque? Oh, you may be. Okay. What are you learning in engineering now? Biomechanical engineering. Oh, that sounds interesting. Okay, but you don't know about the torque. Torque is quite commonly used in engineering, but somehow. All right. Torque is a kind of new, like it's some physics term. Like you can remember, you can think about the first time you learned about momentum. Torque is like, the momentum, yeah. I'm assuming that the moment you learned about momentum was a nightmare because you were so confused about, hey, what the hell is momentum? How is it different to force? Yeah, because both of them looked very similar, that momentum is P equals to mv. And you'll be like, what the hell is mv? Because we learned that F is like ma. They looked very similar, but once you realize that force is talking about change in direction, change in velocity. Yeah, so, and the momentum is about like in a constant velocity. So there is actually a difference between these two. Well, today's lesson is not about this momentum and the force. What I'm going to talk about today is the difference between torque, something called torque, to the force. Torque, using the symbol, the T, like this, is a Latin, okay, is defined as this. It's given here. Torque is the summation of F times R times sine theta. But what the torque is a physical quantity in the first dot point here, physical quantity which produces rotation in an object. So let's think about the momentum too. Min-chan, when we say, hey, that car has a huge momentum, what makes you think that a car carries a huge momentum? Thinking about P equals to mv. If the car carries a huge momentum, it's either had a greater mass, a huge mass, like rather than you're talking about motorcycle, motorbike, we're talking about truck, or greater velocity, is moving really fast. In case you have either heavier or the faster the object is moving, we can say that carries a huge amount of momentum. Kind of makes sense about the momentum too. Now, torque is working very similar to the momentum too. It's like you can understand as this is like some sort of the momentum too. Torque is also known as the turning. Torque is also known as a turning effect. So, in other words, greater the torque means that it's the same as the greater the turning effect. Greater the turning effect too. Then let's think about the situation where we have a rotating wheel. There's a wheel like this. Okay. Now, what I want to do here is I want to rotate that fast. I want to rotate it like in a rapidly. So something called a torque turning effect. If you have a handle here, so you can manually rotate. So you can think about this like the wheel is kind of rotate to the connect to the wheel the handle. Can you picture that? So what you do is you're like kind of rotating, or you can just catch that. You can hold that point in here, point over here, and you can just manually just rotating that. How would you maximize? How would you increase the turning effect?
Increasing the length of the handle.
Increase, sorry?
The handle.
The handle. So first thing you can think of here is rather you get too close to the wheel, okay? You probably use something like a leverage. Try to use a leverage effect. So extend the length of the lever, okay, and then try to rotate with the minimal impact, minimal effort, like this. That's one thing. What about the amount of the force you are going to apply to the wheel? Do you think the greater, as you're running faster, you're rotating faster, do you expect the wheel rotating faster too? Yeah. So we can think about, hey, the turning of the wheel will depends on first of all, it will depends on the amount of force you apply to it. Does it make sense? Okay. The torque will also be related to, think about the smaller wheel to the bigger wheel. Yeah, the bigger wheel, the bigger the wheel means like it's easy to create a turning effect compared to smaller. So it also relates to the radius too. So how do we define that? The torque is known as, combining these two, can be calculated by the product of the F times the R. But the R is not the radius of the circle in that case. It will be the length of the leverage. So for example, you can think about the situation of here. Example torque on page 90 here. A mechanics applying the torque to lift. This is one example. The leverage is one example of torque. Okay, have you ever done this before? Or have you applied the leverage? Try to use the leverage effect too. Not in your life ever. Okay. Yeah, it's not too easy. Yeah, this is. It's a good thing you don't have any experience of this. Okay, that means that your car the tires might get punctured. It's not a good experience. But assuming that you need to lift a car like that, so you need to lift it up, means that, hey, Mincha, I don't think you're gonna hold here, near at the wheel, near at the car. Why? Because you know that in your experience, in your common sense, that hey, if I hold that here, I don't produce much effective energy. I don't really produce effective. You don't really transfer the energy effectively. So the longer the leverage, you can imagine, easier to lift it up. Okay. Also, when you are putting some force, are you putting the force in which direction? Are you putting the force in this direction, number one, or this direction, number two? Which will be more effective? Are you pressing it down, or are you pushing the lever when you want to lift it up?
Down.
We're pressing down. Because when you're pushing, it doesn't do anything with the lifting up. There's no turning effect at all. There'll be no leverage effect at all. So the maximized effect can be produced by when you're pressing the lever in perpendicular, like a hold perpendicular down or up. Okay, greater the angle, if you place it in this angle like that, well, better than number one, but still not be effective as number two. So this is why you can bring up some trigonometry. That is equals to the sine theta, where the theta is the angle made by these. Okay, the norm to the normal, so you apply to the force and the force of the arm too. Let's think about a different situation too. Example 2. The spanner is a good example of a turning effect as well. Now, can you think about the point here? So when you want to rotate the nut, then you need to apply the force in this direction. This is the direction of the force. Okay, that would be direction from the lever here. That would be R there. The angle would be that in between R, the arm of the force, and the arm of the lever, and to the force, like that. So what you expect is by applying that kind of force, you are making the turning effect of the bolt. So you can undo, or we can do the bolt like this. Another example is on the moving wheel. Now moving wheel will be very interesting too. You can see that the force is applied to this direction. If if there is a wheels moving forward, like moving this direction like this, apply the force on that would be going this direction there. Yep, that means that the lever from the center here, that would be the R, which in that case is the radius of the wheel. And you can think about here, if you have a greater, the bigger size the wheel, the greater the size, do you think they can have the greater turning effect? Thinking about the wheels of the your bike, the kid's bike, compared to like wheels of the truck. Okay, for the wheel, the truck wheel, only one rotation can produce huge amount of the force too, compared to the toy wheel. They don't produce much of the turning effect. So in case you have a bigger the wheel, greater turning effect, greater the rotation. Okay, so I know this sounds very confusing. I'm not talking about force first of all. I'm talking about the turning effect. This is kind of confusing. And torque is also related to the module 6 later on when you learn about the motor effect too. So just get the contents about the motor torque today. All right, let's talk about some. Let's see some question 3.9, question 1. A bus driver applies the force of the 45 newtons on the steering wheel of the bus as it turns the right-hand corner. The radius of the steering wheel is at 30 centimeter. If the force applies at 90 degrees, was applied at 90 degrees to the radius, calculate the torque on the steering wheel. So it's not about the bus or the truck. It's a bus. Okay, the bus is a centripetal force. Is the force applied individually applied onto the wheel of the bus. So what you can tell is the wheel is applied in a radius of the 30 centimeters like this, and there's a force applied to 45 Newton. Then all you need to do, the torque is simply equals to F times R times sine theta. Then bring it up, F equals to 45, apply the force on the wheel. R is equals to 30 centimeters, to convert it into the meter, 0.3, times that 90 degrees, that would be sine 90. By the way, sine 90 is 1. So you can just simply calculate 45 times 0.3. That would be 13.5. The unit, okay, the unit of torque, as we are calculating, multiplying force and the radius. Force unit is the Newton, and the radius unit known as the meter. So it'll be unit. We still follow that. Newton meter is a unit of this torque. Okay, that's question 1. Question 2. A force of the 255 Newton is required to apply a torque on a sports car steering wheel as it turns left. The force applied at 90 degrees to the 15.5 centimeter radius of the steering wheel. Calculate the torque. Now let's do that as well too. So we can bring it up. The torque is equals to F R sine theta straight away. The force is given as 255 newtons times that. The radius of the steering wheel is given as 15.5, that's 0.155 times the sine theta, so sine 90. Okay, very simple. So 255 times 0.155, that would be 39.525. So it's 39.5 Newton meter in 3 seconds. So this means that compared to the bus wheel, the sports car has this much a turning effect. It has a greater turning effect. So you can interpret that as just like a momentum. Greater the momentum means what? Either greater the mass or the faster the speed. So you can interpret that as greater the torque, greater the turning effect means that they'll either be turning faster. You can imagine from the sports car's wheel compared to the bus driver. All right, could you try to do 3 and 4 too, please? Okay. Easy. Question 3. Okay. Student uses a 42 centimeter long adjustable spanner to loosen a butt on her bike. Butt? Or like, okay. Should be a bolt. She applies the force of the 65 Newton at an angle of 68 degrees to the spanner. Okay. Calculate the anti-clockwise torque that the student applies to turn. To the nut. Sorry, to the nut. Oh, okay. She said nut. Typo. All right, so R is given as 42 centimeter adjustable. So assuming that the student is holding it at the edge, the end of the spanner. So 42, so 0.42 meters given. Force applied on the spanner is a 65 Newton to create the turning effect. But the angle was given as 68 degrees like this. So turning effect, torque can be calculated by F times R times sine theta. That's 65 times that 0.42 times sine 68. Okay, and Aaron, what'd you get? 25.3. Yep. Newton meter in the anti-clockwise direction. So one more thing, torque is actually a vector quantity. It's a vector. So when you know the direction, you need to talk about the direction of the torque as well. It's quite common that students missing the direction of the torque, so that they lose 1 mark. In that case, we know that's anti-clockwise. Means that there are a turning effect applied in the anti-clockwise. All right, question 4. A mechanic uses a 17 centimeter long spanner to tighten, sorry, there should be a nut on a winch. He applies the force of the 104 newtons at angle of 75 degrees to the spanner. Okay, calculate the magnitudes. So again, torque will be equals to amount of the force applied, 104, times the 2. Starting from the FR sine theta, is 104 for the applied force. R is 17 centimeters, 0.17, times the sine theta, which is sine 75. And Minjun, what'd you get?
17.2.
Get 17.1? 0.2? Why did you get 0.2?
Oh,
0.1. Okay. So question just simply asking the magnitudes, so it'll be Newton meter in your final answer. Easy, yeah? So it's all about the torque. Now, let's talk about the very special case of torque like that. This is called the momentum couple. So when we have a torque of the wheel. So in that case, let's assume that there we have a wheel or kind of motor, for example. It could be a motor too. When something's rotating in one direction, okay, what we have to see for is we have to see from the center of the rotation to the end point where the force is applied. So you can assume that I'm rotating this pen by lifting this cat up, and pushing this down. So as I do so, I'm making a kind of circular motion, making a turning effect like this. But the thing is, I'm applying the force upwards on this side here, okay? Not only that, I'm pushing this down. If I just apply the force upward by holding, okay, you can imagine, I'll show you with the ruler, the bigger ruler. Whilst I'm holding the point in here, okay, just pressing this up or pushing this down, okay, what I'm making is I'm making a big circular motion, or making a bit of a part of the circular motions like this. Okay, you have to see like I'm holding that tight and then making the turning effect like this. Yep. In that case, it's pretty easy to calculate the torque. That I know that'll be the R, that'll be the force applied, and if I should apply it in 90 degrees like this will be my torque. Now, questions like this is kind of different. What I'm doing is I'm holding the center. Okay? And what I'm doing here is I'm applying the force upwards from this direction here and downwards in this direction there. Do you see the difference between holding the edge and making the rotation too? Then what happened to this situation here? Yeah? So it means that this is with the pivotal point, and as I'm applying the force upwards and by the same time force downwards in the opposite direction, making a rotation like this. Can you guys see that? Okay. Now, by thinking about the torque too, from the center here, as we learned, that was the torque. Yeah. But in here, as I'm applying the force, two different forces on the opposite side like that, there will be two types of the turning effect will be applied. One is the torque applied from here, torque 1, another torque applied from here, torque 2. And assume that the same radius R. Does it make sense to everyone here? You need to see the difference between this to this. So in case you have a central point as a pivotal point and pushing up and down, there will be the separate torque applied by making the total net torque applied onto the, it could be the motor or the wheel too. So how to find that torque? It'll be easy. We know that assuming that is a diameter, the D is given, like that too. Then torque applied on torque 1 would be the F times the half of the D, only half of D, times that sine theta, assuming there's a 90. Means what would be the torque applied on this side there then?
Minus F times 1
D times sine theta, which is 92. So what you found out here is these two torque, assuming that we apply the same amount of the same magnitude of force here, they would have the same magnitude of torque, but direction, that would be upwards. And this would be down. I know it's kind of common sense, like, oh yeah, that's of course like, yeah, this will be up and down. So that's why I'm making the torque or turning effect that too. The reason why I'm giving you that question and giving here is because you get questions like this. And this is related to the module 6 as well. Yes, you're learning about the motor in the module 6. So as you can see here, if you have a rotation here, so I'm going to show that the diagram again like this. When you're holding something, and holding that with the mass of that, do you see like, what I'm doing is I'm kind of rotating this, the rotor, I'm going to call it, or the motor, to make the lift that up. Can everyone see that? Okay. Now, Donghyun, what would be the force applied on this wheel, the rotating wheel? If we know the this is the M.
It will go down.
Yeah, assuming that like they're maintaining, like we're just holding, they're maintaining. But I'm still rotating that and rotating this, but this is kind of maintaining the same height. Doesn't that mean that the tension, there will be the force, gravitational force pushing this down, but there will be a tension force. They're holding that up. So that masses look like it's hanging, it's not really moving, even though I'm rotating the rotor. Or you can think about a situation where you're holding something, holding the wheel, the toy wheel, not making to return. That means the amount of force you apply to the wheel will be the same amount of the force applied by the torque, the motor too. So in that situation here, if I could find the torque of this rotating wheel, should we consider to be a whole radius? Or which side will be the side that applying the turning effect, Irene, in here? Which side of the rotor is applying the turning effect in that situation? Yeah, well, it will be from the center to the side we're touching that wire. Okay, making a perpendicular angle. As you can imagine, ignore that, ignore the wheel structure there. It will be something like this. That this is part over here. You can imagine this is a rotating part, the rotating bar. It's kind of lifting up. Kind of lifting up. You can imagine lifting up. So what we do is making it into a circle. So that part over here, which is the R, the radius R, will only be considered to calculate the torque of the rotor. Okay? Or you can just imagine like by hanging this mass like this. Means if I just hang the mass, assuming that the motor is not functioning now, okay? But hanging the mass on at the end on the motor here, what do you expect for this? Will fall down as there's some force applied there too. Now the side that applying the force will be there will be force applied downwards here. What is this? It's exactly the same situation here. Okay, I'm not considering the diameter, because by the time I'm placing the force downward here, there will be force applied upwards here too. Yeah, but when we are considering the torque, torque will simply be half of the diameter again. Yeah, half of diameter times the 2, force applied, which is mg. Angle made by the wire, the string to the rotor will be 90, so the sine 90. This is a very special situation that we're using the half D because we have rotation. Remember the rotation of the both sides going up and down at the same time, the couples. Okay, unlike the spanner. Spanner is basically we're just using up or down from the pivotal point. Okay, in the case you have a pivotal point in the center, you need to concern about there's only that radius from the center to that point you expect applying the force will be counted for the torque calculation. Kind of makes sense? Kind of makes sense, okay? This is related to module 6 as well in the motor parts. So let's do that questions. The mass of the box hang the motor is 10 kilo. What is the minimum torque required to lift the box if the diameter of the rotor is 50 centimeters? Let's do that. So we're given that the diameter, the mass is given at 10 kilo. Diameter is 50, so the radius we're touching that part would be half of the 50, which is 25 or 0.25 meter. Yep, and then what we know is the side we're touching them is kind of perpendicular. So the angle is 92. So torque would be what? Fr sine theta. The force is now given as the mg, so 10 times 9.8 times that radius, 0.25. So that's basically 25 times 9.8. Then you'd get 245 Newton. Direction. Donghyun, what would be the direction in that case of the torque? If you hang the mass like this, down, or in terms of turning effect, down, yeah, it would be down, or the clockwise. As we know, the mass will kind of pulling the rotation going down like this, in this direction. So making a downward as well as the rotation effect of the clockwise. Yes?
Oh, why is it 245 from 24.5? Because wouldn't it become 2.5?
Oh, just 24.5, sorry. Yeah, misread the answer. Okay, so torque is kind of new things, but you know, as you can see, it's relatively simple. I'm just showing the very special case, which is quite common in the HCC as well too. So, could you guys try to do some try yourself questions 1 to 5 on that page 96, please? They are like couples, yes.
What are the two different?
Hmm? Two force. Hmm?
If it was this situation.
Sorry, I can't.
If it was like the two, then it would be like, they're both different.
There will be like, yeah, the one turning if they actually the total net effect would be the whole net force value given. Yeah. Yeah. Try up to question 5. Give you just 5 more minutes. Okay, question 1. Use the concept of torque to explain the following. A. It is easier to open a heavy door by pushing it at the handle rather than in the middle of the door, which is true. Why? The magnitude of torque will be increased as you increase the R value. So increased R, as we know the torque is the F times R times the sine theta. Increasing the R from the further away from the handle will be increase the torque, which means that it will be less. For that, the door, you have a fixed turning effect, means that you need to apply the less force than that. Okay. All right. B. Calculate the torque exerted on the roundabout. The shown include the direction of the appropriate. So we have the given that the torque can be just simply calculated by. Sorry, I didn't do the B. It is possible to move the very heavy rocks in the garden by using a long crowbar. Yes, as you're using crowbars, you're using the large long crowbar can be generating the large torque as well too. So you're working as a kind of leverage effect. So what you just need to be careful is using the large bar means you need to push that in the further distance, give greater R, not in the near at the pivotal point. Question 2. Calculate the torque exerted in the roundabout. Okay, so question 2A, simply calculate that. All right, we're given that 2 meters, we apply that, and F is going like this direction. So what we have to concern is as the forces applied in this direction, okay, so we got to think about this. Torque is equals to F times the R times the sine theta. In that case, you are producing the inserting the force. Yeah, okay, 100 times 2 times sine 90. So you should get 200 Newton meter. Now direction, as it's moving upwards like this, it'll be the anti-clockwise, making the turning effect anti-clockwise. B, the direction is we have a 1.5 the radius, but 200 Newton for the force, but the problem is the theta is 0. Therefore, the torque applied to that is 0 too. Good. 3, the magnitude of the torque required to tighten a bicycle wheel is 15 Newton meter. Calculate the force arm required to if a 30 Newton force is applied to perpendicularly. So what we have to concern is assuming that angle is a 90 and the torque is given as 15. So as a torque equals to F times R times sine theta, and we're given the 15 is a torque and the force is applied to that is 30 times R. Therefore, R must be 0.5 meter in that case. Easy. Question 4. Student pushes a heavy door at the point of there is a 50 centimeter from the hinge, such that it creates a torque of 9 Newton meter. With what magnitude of the force does the student push? Assume the student pushes a perpendicular. So again, the angle is given at 90 degrees. Then torque is given as F times R times sine theta. What we are given here is torque is given as 9. And we applied the force unknown, but applying the amount of the 0.5 like that. And did you guys get the F equals to 18 Newton? Yep, easy question. Question 5, the last question. Spindle with a length of 40 centimeters is used to tighten a nut on the car wheel. If the magnitude is of the perpendicular force applied 225 newtons. Calculate the magnitude. Didn't we do that question? I feel like we did that question during the ink exercise. I think we did. Okay, but we can do that, redo that again. F equals to, torque equals to F times the R times the sine theta. That is 225 times the R, which is 40, was 0.4. Then you should get the 90 Newton meter for your final answer. Easy. Okay, the torque. But don't think about like torque. Oh, torque is very easy because you have just to substitute the values in. Yes, Yes, you won't get really complicated torque question in Module 5 yet, until it's combined with the Module 6 later on. Okay, so for today's lessons, I want you to understand about the different type of the circular motions again. So about like there's different types of circular motions, pendulum, bankings, or the going up and down hills too, and even for the torque too. This is not so closely relevant to the circular motion, but still using circular pathway too. So again, torque is a very similar to like something about the momentum versus the force too. Just thinking about greater turning effect means that greater the turning of the wheels, whether with the wheels or the leverage too. Any questions about up to chapter 3? So this is the end of the circular motion now, finally. We finished the circular motion now. It's been like 5 weeks.
This will be on the topic of drive.
Yes, this is why I finished that topic today. Make sure you revise those chapter 3, all whole chapter 3. I know the content itself is not so complicated. So module 5, chapter 1 and 2, projectile and circular motion, they are doable. I mean, they should be doable. If you don't really understand some of the contents, that means you need to think about the module 1 and 2 contents. But it should be all right. And then in your holiday, yes, next week, so what day are you coming back? Next Tuesday?